This project daisy chains together 4 Moreland bar graphs, allowing the output of 32 individual LEDs using only 3 pins from the ATtiny85, the clock, data, and latch pins. When chaining shift registers together, each register's carryout is connected to the input of the next register in the chain, allowing the bits to be shifted from one register to the next. Data is serially entered to the shift register by placing the bit to be entered on the data pin and synchronously providing a rising edge on the clock pin. Since the 595 is composed of 8 daisy chain D latches, this process is simply repeated 8 times to shift out a byte and 32 times to shift out 4 bytes. Once all 32 bits have been shifted in, a rising edge on the latch pin of all 4 shift registers transfers the internal latch into the parallel output LEDs.
As opposed to writing new functions so that different lengths of binary numbers can be displayed, a technique called overloading functions is used. Here there exist multiple functions with the same name but with a different data type for the value parameter. This way, when a uint8 is set to equal the value, calling the outshift function calls the uint8 function, but when the value is a uint16 or uint32, it calls the corresponding outshift function which contains multiple uint8 shiftouts. To avoid ambiguous calling of functions, casting lets us pass a variable as a data type different from what it currently is, whether that means shrinking it or adding zeros to it. For example, in the uint32 function, the original uint32 must be cast to a uint16 so that just 16 bits are grabbed, and the correct function is called. Last, this project explores creating a library to store the outshift functions so that the library can simply be included in any sketch and the functions can be called. To make this possible, addressing and pointers are used to include the port as a fifth parameter. With this, the entered port when calling the function is passed as an address using an ampersand, which is carried through to the uint8 function, where the contents of the address are changed by pointing to the data inside the address with an asterisk.
Previous versions of the Moreland bar graph dealt with the hot dog bun to hot dog problem of a mismatched number of LEDs on the bar graph to the number of output pins from the shift register. This meant that 2 LEDs on the bar graph could not be used when connected to a 595 shift register. To solve this problem, a new bar graph was designed with only 8 LEDs, eliminating this issue. The design allowed 8 LEDs to be slipped into place inside the bar graph and epoxied to hold them in place. The bar graph was designed in Fusion 360 and printed from resin by JLC. The case was designed with 2mm thick walls, and the width between each LEDs was set so the bar graph could be used on a breadboard. ACES branding was also added to each side of the case, with the designer's names added on each end.
For more flexibility, this project executes the shiftouts using register-level code through masking and the internal registers of the ATtiny85's I/O pins. Essentially, for every I/O pin on our set of Atmel MCUs, there are 3 bits and 3 different registers to control the use and state of each pin. 1 bit is stored in a data direction register to determine if the pin is an output or input, 1 bit is stored in a port register to determine if the pin is going to display a 1 or a 0, and 1 bit is stored in a pin register to hold the value of the pin when it is an input. In the case of the ATtiny85, there's only one set of these 3 registers, and that is the B set. Therefore, DDR-B and port B at bits 0, 1, and 2 are used for this project. All 3 bits in DDR-B are set to 1 so that our data latch and clock pins are outputs, and the 3 bits in the port B register are continually manipulated to execute the shiftout. To change the bits of these registers, masking is used to target single bits and leave the rest unchanged. To clear a bit, or to turn it to 0, the contents of the register are bitwise ANDed with a byte that is all 1s except for the bits to be cleared. Alternatively, to set a bit, or to turn it to 1, the contents of the register are bitwise ORed with a byte that is all 0s except for the bit to be set. For the outshift function, the desired value to be shifted out is masked bit by bit with a for loop to display each bit sequentially on the data pin of the first shift register.
3 32 LED animations were created for this project. The first program uses 2 while loops to continuously shift a 1 from left to right and then from right to left. The loop runs starting at 0 with I increasing by 1 every loop, causing for the number of bit shifts left to increase with the value I. Once I is equal to 31, the value begins to be bit shifted to the right on every iteration. The other 2 animations work similarly, with one of them indexing an array at I, which increases each time. The array of 32-bit numbers creates the pattern of curtains closing. Another loop which indexes the array at 32 minus 1 creates the effects of curtaining opening again. The last animation is just the loop of hex A being shifted out and then bitwisely inverted, creating the hypnotizing effect seen here. Thanks for watching.